Hello viewers, welcome to video lecture series on group theory. Myself Sudhakar. In the previous lecture, we solved important short answer type questions related to group and its properties. In this lecture, we shall solve important long answer type questions on infinite abelian group. So the first question is, prove that the set Z of all integers is a abelian group under addition. So instead of abelian group, they may give commutative group. Okay, now what do you mean by abelian group? So we have to verify 5 laws, namely closure, associative, identity, inverse and commutative law. So if they give only group, we have to verify up to 4 laws, that is up to inverse law. Okay, now we shall prove this. So we shall consider this given set. The given set is Z. We know that Z means set of all integers. What are the elements? 0, plus or minus 1, plus or minus 2, plus or minus 3, etc. It is an infinite set. Okay, our aim is to prove that Z is a abelian group under addition, or we can write Z plus is a abelian group. So the first law is closure law. So what is closure law? So in the given set, if you take any two integers, and if you add sum of those two integers must belong to the given set. So for example, if I take 2 and 8, if we add 2 and 8, I get 10, and we have to check whether it belongs to given set. Yes, it belongs to. Similarly, if you take any two integers, sum must be in Z. So we shall write in general, since sum of any two integers is also an integer, we have a plus b belongs to Z for all ab belongs to Z. And the next is associative law. So again we know that the sum doesn't alter if you interchange the brackets. So if I take 1 plus of 3 plus 5, is it equal to 1 plus 3 plus 5? Okay, let us check. This is 1 plus 8, that is 9. Similarly, this is 1 plus 3, 4, 4 plus 5, 9. Okay, I got LHS equals RHS. And it is true if we consider any three elements from the given set. Therefore, it is clear that a plus of b plus c is equal to a plus b plus c, and it is true for all a, b, c belongs to Z. Therefore, associative law is satisfied. And the next law is identity law. So identity law means we have to find the identity element. Consider an element minus 9. So what is the element I should add so that I get minus 9 itself? So clearly it is 0. So whether 0 belongs to Z? Yes, 0 is in Z. And it must true for every element. If I take any integer, if I add 0, I should get same integer. Again it is true. Therefore, 0 belongs to Z is the identity element. Why 0 is the identity element? Because a plus 0 is equal to 0 plus a, and it is true for all a belongs to Z. So the next is inverse law. So inverse law means we have to find inverse for every element in the Z. So if we consider 10, what is the element I should add so that right hand side I get identity element, that is 0. So the element is minus 10. And you have to check whether minus 10 belongs to the given set Z. Yes, it belongs. Therefore, minus 10 is the inverse of plus 10, and vice versa. 10 is the inverse of minus 10. Similarly, what is the inverse of 100? Inverse of 100 is minus 100. Inverse of minus 120. What is the inverse of minus 120? Plus 120. So if you take positive, the inverse is negative of that. Okay. we shall write, for every A belongs to Z, there exists an element minus A, because A minus A, I get 0, that is the identity element, such that A plus of minus A is equal to minus A plus A is equal to 0. Here we call minus A is the additive inverse of plus A and vice versa. So if you prove up to inverse law, we can conclude that Z plus is a group. But the given question is abelian group. Therefore, we shall continue. So the next law is commutative law. So commutative law means if I consider any two integers, 12 and 8. So 12 plus 8, is it equal to 8 plus 12? Yes, we know that it is true. Therefore, A plus B is equal to B plus C, and it is true for all AB belongs to Z. So we have verified all the 5 laws. So we shall conclude that Z plus is a abelian group. And we note that Z is an infinite set. Therefore, we can write Z plus is an infinite abelian group. So if they ask, prove that Z is an infinite abelian group under addition. So after this, we shall add a sentence. Since Z is an infinite set, therefore Z plus is an infinite abelian group. Similarly, we can prove that Q plus is an abelian group, and also R plus is an abelian group. We shall move to next question. Show that the set Z of root 2 is equal to A plus B root 2 such that AB belongs to Z is a abelian group under addition. Again, abelian group means we have to verify all the 5 laws. So before that, we shall understand what are the elements of Z of root 2. So in the proof, we shall write the given set Z of root 2, where Z of root 2 contains elements of the form A plus B root 2, where AB belongs to Z. So what are the elements of Z of root 2? So here you can see what are A and B. A and B are integers. So dash plus dash root 2. So this we have to fill up by writing the integers. So any integers we can write. So minus 5 plus 2. So what we got? Minus 5 plus 2 root 2. This is an element in Z of root 2. Similarly, 19 minus 3 root 2 belongs to Z of root 2. 2 plus 5 root 3. This is not an element in Z of root 2 because here we must have root 2. Okay. Similarly, if I take 9, whether it belongs to Z of root 2? Yes, because 9 can be written as 9 plus 0 root 2. Okay, all the integers we can express in this form. Therefore, all the integers belongs to Z of root 2. And also note that if you take 5 by 2 plus 4 root 2, again it is not an element in Z of root 2 because we got a fraction here. So both numbers, these two numbers must be integers. I hope you understood what are the elements of Z of root 2. Now our aim is to prove that Z of root 2 is a abelian group under addition. So before considering the first law, I have to consider maximum. How many elements required? So in case of associative law, we require 3 elements. In all other laws, we need only 2 elements. That's enough. So we shall consider 3 elements in general. So I take let x equal to A plus B root 2 and y is equal to C plus D root 2 and z is equal to E plus F root 2, where A, B, C, D, E, F are the elements of Z. And here you can consider x is equal to a1 plus b1 root 2, y is equal to a2 plus b2 root 2, and z is equal to a3 plus b3 root 2. You can consider in that way also. Okay, the next we shall consider the first law, that is closure law. So here I have to consider any two elements and I have to add, and we have to look at the result whether it belongs to z of root 2. So we shall consider x plus y. You can consider x plus y, or you can consider x plus z, or you can consider y plus z, etc. So consider x plus y. So what is x? X is a plus b root 2. And what is y? Y is c plus d root 2. Okay, now in the next step we shall add the rational part. We shall group rational part and irrational part separately. Therefore, this is equal to a plus c plus b plus d root 2. Therefore, it is of the form, now you see, a is an integer, c is an integer, therefore a plus c is an integer. Similarly, b is an integer and d is an integer, therefore b plus d is also an integer. Therefore, it is of the form integer plus integer root 2. Clearly, it belongs to z of root 2. Therefore, x plus y belongs to z of root 2 for all xy belongs to z of root 2. Therefore, closure law is satisfied. Next, we shall consider associative law. So, in case of associative law, under addition, we know that a plus of b plus c is equal to a plus b plus c. What are ABC? ABC are the elements of the given set. Here we have taken the elements of the z of root 2 as x, y, z. Therefore, what is the left hand side of associative law? X plus of y plus z. Okay, we have to prove that x plus y plus z. That is right hand side. Okay, let us see. So, what is x? X is a plus b root 2 plus y. Y is c plus d root 2 plus z. Z is e plus f root 2. And this is equal to a plus b root 2. So, here we shall add the rational parts. Rational parts means c plus c plus d plus f root 2. So, we shall group these rational and irrational parts separately. Next, this is equal to, so again we shall regroup, rearrange the terms. So, a plus of c plus c, so the rational part, and what is irrational part? B plus of d plus of into root 2. Okay, now we know that A, C, E and also B, D, F. What are A, B, C, D, F? Are all integers. And just now we proved integers is a abelian group under addition. Therefore, it satisfies associative law. Therefore, a plus of c plus e can be written as a plus c plus c. Therefore, we shall write a plus c plus c. Similarly, b plus d plus f root 2. And again, this can be written as a plus c plus b plus d root 2. Okay, we shall group that one. And remaining is e plus f root 2. Okay, again we shall rearrange the terms here. So, a plus b root 2 plus c plus d root 2. And the last term we shall write as it is e plus f root 2. So, what is a plus b root 2? That is x, and c plus d root 2 is y, and e plus f root 2 is z. Therefore, we get x plus y plus z. Therefore, we have proved x plus of y plus z is equal to x plus y plus z for all x, y, z belongs to z of root 2. Therefore, associative law is satisfied. So, next is identity law. So, again we have to find identity element. If you consider an element, for example, 2 plus 3 root 2. This is an element in z of root 2 plus, so what is the element I should add so that I get same element, that is 2 plus 3 root 2. So, the number is 0, and the question is whether 0 belongs to z of root 2. Any element in z of root 2 is of the form a plus b root 2. Whether 0 belongs to z of root 2? Yes, 0 belongs to z of root 2 because 0 can be written as 0 plus 0 root 2. So where here in this place we must have an integer, in this place also we must have integer. 0 is an integer, therefore 0 can be written as 0 plus 0 root 2. Clearly it belongs to z of root 2. Therefore if you take any element from z of root 2 and if you add 0, I get same element. Therefore 0, which can be written as 0 plus 0 root 2, which is an element in z of root 2, is the identity element, because x plus 0 is equal to 0 plus x, I get x. And it is true for all x belongs to z of root 2. Therefore, identity law is satisfied. So next we shall consider inverse law. Again, inverse law, I have to find whether we have inverse for every element of z of root 2. Again, I consider same element 2 plus 3 root 2. So what is the element we should add so that right hand side I get the identity element. Identity element is 0. So what is the number we shall add for 2 plus 3 root 2 so that I get 0? That number is minus of 2 plus 3 root 2, negative of this number. Whether it belongs to z of root 2, minus of 3 root 2, minus of 2 plus 3 root 2. So that is minus 2 minus 3 root 2. Again, clearly it belongs to z of root 2. So here you see minus 2 minus 3 root 2 can be written as minus 2 plus of minus 3 root 2. Minus 2 is an integer, minus 3 is an integer. It is of the form a plus b root 2. Clearly it belongs to z of root 2. Therefore, for every element, if you consider, we can find the additive inverse. So another example, if I take minus 5 plus 3 root 2. So what is the inverse of this? 5 minus 3 root 2. So you write the opposite sign. Therefore, both get cancelled. If you add, I get 0. Therefore, for every x is equal to a plus b root 2 in z of root 2, there exists minus x, negative of that. That is minus of a plus b root 2, or we can write minus a minus b root 2, which belongs to z of root 2, such that x plus of minus x is equal to minus x plus x is equal to 0. So here minus x is the inverse of plus x, or we can say minus x is the additive inverse of plus x, and vice versa, x is the additive inverse of plus x. So inverse law is satisfied. So the next is commutative law. So how can we prove commutative law? What is the left hand side of commutative law? X plus y. So consider that x plus y, we shall replace x and y, that is equal to a plus b root 2 plus y is c plus d root 2. So we shall group the rational part a plus c and irrational part b root 2 and d root 2. So what we got, if you group the terms, we get a plus c plus b plus d. Common is root 2. So we have written b plus d root 2. So what are a, b, c, d? We know that a, b, c, d are integers. So integers is an abelian group. It satisfies commutative law. Commutative law means a plus c can be written as c plus c. So in the next step, we shall write c plus a instead of a plus c, and d plus b instead of b plus d. So why we have written? Because z satisfies commutative law. So again we shall rearrange the terms. Next step we shall write c plus d root 2, that's the first term, and the next term is a plus b root 2. So we get c plus d root 2 plus a plus b root 2. C plus d root 2 is nothing but y, and a plus b root 2 is nothing but x. Therefore this is equal to y plus x. What we have considered left hand side, that is x plus y. Therefore we have proved x plus y is equal to y plus x, and it is true for all xy belongs to z of root 2. Therefore commutative law is satisfied. Therefore we conclude that z of root 2 is an abelian group under addition. So writing z of root 2 comma plus is a abelian group. Similarly, you try these problems. Show that the set z of root 3, where the elements of Z of root 3 are A plus B root 3 such that AB belongs to Z is a abelian group under addition. So in the examination they may give Z of root 3 or another problem Z of root 5. You can see here what is Z of root 5. It is the set of all elements of the form A plus B root 5. Similarly, another problem Z of root 7, A plus B root 7. So only thing is you should change wherever in place of root 2, we have to change root 3, root 5, root 7, etc. So we can verify these sets are abelian group under addition. So the next question is, show that this set Z of I is equal to set of all elements of the form A plus IB such that AB belongs to Z, where I is equal to square root of -1 is a abelian group under addition. So what is Z of I? Z of I is called as the set of Gaussian integers. Okay, we shall prove this. What is given set? So always you must be very careful. Whenever the problem is given, note the given set and what is the binary operation. So given set is Z of I. We shall write Z of I is the set of all elements of the form A plus IB, where AB are integers, and we have to prove it is a abelian group under, what is the operation they have given? Addition. So our aim is to prove Z of I is a abelian group under addition. Again, we require how many elements? Maximum 3 elements. So we shall write let x equal to A plus IB, and y is equal to C plus ID, and z is equal to E plus IF, where A, B, C, D, E, F are all integers. Similarly, you can take x is equal to A1 plus IB1, y is equal to A2 plus IB2, and z is equal to A3 plus IB3, and you can write where A1, B1, A2, B2, A3, B3 belongs to Z. Okay, we have taken 3 elements from Z of I. Now we shall consider one by one. The first one is closure law. So closure law means we have to consider sum of any 2 elements of Z of I. You can consider any 2, either x plus y or y plus z or x plus z. So we shall consider x plus y. What is x? X is nothing but A plus IB, and y is nothing but C plus ID. Okay, here. So we shall group the terms. So A plus C, and imagine what is imaginary part? B plus D. So B plus D, what's the common factor? I. So I have A plus C plus I of B plus D. So what is A plus C? A is an integer, C is an integer, therefore A plus C is an integer. Similarly, B is an integer, D is an integer, B plus D is an integer. Therefore, it is of the form integer plus I into integer. So it is of the form A plus IB. Therefore, clearly it is an element in Z of I. Therefore, x plus y belongs to Z of I for all xy belongs to Z of I. Therefore, closure law is satisfied. So the next is associative law. So we shall consider the left hand side of associative law, that is x plus of y plus z. So we shall replace what are x, y and z. X is A plus IB plus of what is y? Y is C plus ID, and z is E plus IF. So in the next step, so whatever we have in the flower bracket, we shall group the terms, so real and imaginary part separately. Therefore, next step, this is equal to A plus IB plus of C plus E, that's the real part, plus I into D plus F. So again we shall rewrite this, that is equal to, we are rearranging the terms, A plus of C plus C plus, so group the terms, that is imaginary parts, that is I into B plus of D plus F. So again A, B, C, D, F are all integers. Integers satisfy associative law. Therefore A plus of C plus E can be written as A plus C plus E, Similarly, b plus of d plus f can be written as b plus d plus f. Therefore, again, this is equal to, so a plus c plus I times of b plus d plus, so the next term is e plus I into f. So we have rewritten this step, and this is equal to, again rewrite, this is a plus I into b. So that's the first term. Next, c plus I into d. See the next term. And the last term you write as it is, that is e plus if. So what is a plus ib? A plus ib is nothing but x, c plus id is nothing but y, and e plus if is nothing but z. Therefore we get x plus y plus z. Therefore we have proved x plus of y plus z is equal to x plus y plus z, and it is true for all x, y, z belongs to z of I. Therefore associative law is satisfied. Either you can prove by considering left hand side and right hand side separately. In that way also you can prove. So the next is identity law. So again, what is the identity element? So we shall consider the elements of any element of Z of I. For example, 2 plus 3i. 2 plus 3i is also an element in Z of I. So what is the element I should add so that I get 2 plus 3i itself? So clearly element is 0, and the question is whether 0 belongs to Z of I. In Z of I we must have elements of the form a plus ib. So 0, can we write 0 in this form? Yes, we can write 0 can be written as 0 plus I into 0. And be careful, these two numbers must be integers. So it is an integer, no problem. Clearly it belongs to Z of I. So if you add 0 to any element of Z of I, you get same element. Therefore I can say 0 is the identity element. So clearly 0, which is nothing but 0 plus I into 0, belongs to Z of I, is the identity element. Why we are saying this is the identity element? Because x plus 0 is equal to 0 plus x, which is equal to x, and this is true for all x belongs to Z of I. So identity law is satisfied. So we shall consider next one, inverse law. So if you consider 5 plus 3i, again what is the element I should add, or what is the number I should add, so that right hand side I get the identity element, that is 0. So clearly I should add negative of this number, that is minus of 5 plus 3i. Minus of 5 plus 3i is nothing but minus 5 minus 3i. Whether it is an element in Z of I, minus 5 minus 3i can be written as minus 5 plus of minus 3 into I. Minus 5 is an integer, minus 3 is an integer, therefore it is of the form a plus ib. Therefore clearly it belongs to Z of I. Therefore minus of 5 plus 3i or minus 5 minus 3i is the additive inverse of 5 plus 3i. Similarly we get inverse for every element of Z of I. Therefore for every x is equal to a plus ib belongs to Z of I, there exists an element minus x, that is negative of that number. So that is minus of a plus ib belongs to Z of I, such that if you add minus x to plus x, therefore x plus of minus x, which is equal to minus x plus x. So what is the answer we get? 0, which is the identity element. Here minus x is the additive inverse of plus x, or we can say x is the additive inverse of minus x. Therefore for every element in Z of I, we get additive inverse. Therefore inverse law is satisfied. So the last law is commutative law. So we shall consider the left hand side of commutative law. So what is that? X plus y. Let us see whether we get y plus x. So replace x and y. What is x? A plus ib. And what is y? C plus id. So write a plus ib plus of c plus id. Again we shall group the terms, real parts and imaginary parts separately. Therefore that is equal to a plus c plus I of b plus d. So we are grouping the terms, real part separately, imaginary part separately. And again we know that A, B, C, D are integers. Integer satisfies commutative law. Therefore A plus C can be written as C plus A, and B plus D can be written as D plus B. So we got this step because Z satisfies commutative law. So again rearrange the terms, rewrite this. So we can write C plus ID, and the next term is A plus IB. So this is equal to C plus ID plus of A plus IB. C plus ID is nothing but Y. A plus IB is nothing but X. Therefore this is equal to Y plus X. Therefore what we proved? X plus Y is equal to Y plus X, and it is true for all X, Y belongs to Z of I. Therefore commutative law is satisfied. Therefore we have verified all the 5 laws. Therefore Z of I is an abelian group under addition. Okay, similarly you can try this problem. Show that the set of all complex numbers is an abelian group under addition. So set of all complex numbers is denoted by C. So what is the set C? It is the set of all elements of the form A plus IB, where A, B are real numbers. Okay, what is the difference between set of all complex numbers and set of all Gaussian integers? Okay, set of all Gaussian integers is the set of all elements of the form A plus IB, where A and B are integers. So you can see here A and B are integers, here A and B are real numbers, and elements look like same, A plus IB. Only difference is AB are real numbers here, AB are integers here. So you can verify the complex numbers is a abelian group under addition. So in the next lecture we shall consider other problems related to infinite abelian group. Thank you.